Welcome to Introduction to Composites. Today is the fourth day of this particular week. What we have developed in the first 3 days of this week are strain displacement relations, relations between stresses and strains for individual layers, and also yesterday we introduced or defined terms known as force and moment resultants, and essentially what they mean physically are that suppose you have a plate and it is subjected to external forces and external stresses, then the relationship between these stresses and the forces and moment it experiences on a per length basis. So, that is what is known as force and moment relations. So, the next thing we want to do is we want to expand this topic further by relating this force resultants, force and moment resultants, and strains, mid-plane strains and mid-plane curvatures. So, this is the relationship we want to develop. So, essentially what we will do today is we will develop the relationship between force and moment resultants and strain mid-plane and mid-plane strains and mid-plane curvatures. So, first we will start with force resultants. So, we have shown that Nx, Ny, Nxy, this is equal to integral it is integral of from minus h by 2 to h by 2 integral of sigma x sigma y tau xy times dz. This is what we have developed. So, we have developed 3 different equations, but here what we have done is we have just combined them into a single vector equation. Now, before we work on this further, we will develop a convention. So, suppose I have a laminate okay, and this is my point A, this is my point D. The mid plane is located here. So, this is z equals 0 and let us say it has n different layers. So, this thing is having several layers. So, layer 1, layer 2 and so on and so forth, and let us say this is kth layer and this is the nth layer. So, this is layer 1, layer 2, layer k and layer n. The overall thickness is h. So, from the mid plane the top point is here h by 2, this is the coordinate of point A, and the bottom one because z is going down positive. So, this is z equals h by 2 and here z equals minus h by 2 on the top layer. Okay. And then we write down the coordinates of the beginning and end of each layer. So, I say that this is h0, this is h1, this is h2. Okay. So, what is the thickness of the top layer? It will be h1 minus h0. What is the thickness of second layer? It will be h2 minus h1. What is the layer thickness of kth layer? It will be hk minus 1 and the other one is hk. So, it will be hk minus 1. And what is the thickness of the last layer? It will be hn and hn minus 1. So, this is the convention we will follow throughout this class. Okay. So, with this convention we develop this relation further. So, we say that Nx, Ny nxy equals, now what we have to do is we have to integrate sigma x across the thickness of the specimen, okay. And we know that when we go from one layer to other layer, sigma x can, and sigma y or tau xy, it can arbitrarily jump, it jump discontinuously because the Q matrix changes, right, because the Q matrix changes. So, and we also know that for a layer, what is stress? Stress is nothing but Q times the strain, okay. So, this integral, instead of having integral, if once we are going from one layer to other layer, we have to add, and within the layer we can integrate, because within the layer the stress is linearly varying, across layers stress jumps. So, once I move from one layer to another layer, I have to add, but within layer I have to integrate. So, using this thinking, I can say that I have to integrate this thing, add this thing 1 k times, k is equal to 1 to n. If there are n layers, then I have to do n additions, and then within each layer I integrate it. So, let us say I am integrating it for the kth layer. So, it will be h k minus 1 to h k, and what is the, for the kth layer, what is the stress? It is q bar times epsilon, excuse me, epsilon x, epsilon y, gamma x y plus z times k x, k y, k x y. dz, okay. So, this is what I get. So, essentially what I have done is, first what I have done is I have developed the stress strain relations for the kth layer, and I am integrating this on the kth layer, and the range of z is hk minus 1 to hk, because those are the coordinates for the top and bottom surfaces of kth layer, and then for I do similar operations for each layer and I add all of them up, okay. And this subscript k indicates that this is for the kth layer, q bar is for the kth layer. So, this is what I get, okay. And this entire integration is happening for over this variable z, okay. Now, we know that epsilon x naught, epsilon y naught, gamma x y naught, they do not change with z, kx, ky, kxy, they do not change with z. Also within a layer q bar is constant, because the same thing, and because I am integrating this layer by layer. So, within a layer the only thing which gets involved in integration is this thing z, right. So, when I integrated this z becomes z square by 2, and here I get, and when I integrate the mid plane strain vector I get another z term here, okay. So, when I integrate this, what I get is, so this is equal to k is equal to 1 to n, and q bar times h k minus h k minus 1 times epsilon naught bar. So, this is epsilon naught bar and this is k naught bar, k. So, I am just, for purposes of brevity I am just doing this. How did I get hk minus 1? See, there is a 1 here, you can consider, when I integrate 1 with respect to z, I get z, and when I take the limits z from hk to hk minus 1, I get hk minus 1. Okay. And this is for the kth layer. We are still doing this for the kth layer, and then I do the same thing with the other one. So, I get q bar for the kth layer, and when I integrate z, it becomes z square by 2, and when I take the limits hk to hk minus 1, I get hk square minus hk minus 1 square by 2 times the mid plane curvature for the kth layer, and this entire thing I do for every single layer and I add it up. This entire thing operation for every single layer and I add it up. Now, across all the layers the mid plane strain does not change. Mid plane strain is because it is at mid plane strain. So, essentially what I have to do when I am adding this up is I do not have to worry adding up epsilon naught is common, same thing in this term k naught is common. So, I have to add up products of these for individual layers. Okay. So, essentially what I get is, now this is a 3 by 3 matrix and this is just a number. So, when I add multiply this and I add this for all the layers, I still get a 3 by 3 matrix, and I call that 3 by 3 matrix A matrix. Okay. So, that is equal to a 3 by 3 matrix A times the mid plane strain. So, from here I get A. Okay. And same thing I do on the second one. So, here this is a 3 by 3 matrix, and hk square by 2 minus hk minus 1 square by 2 is a number. So, when I multiply that and I add up all the consecutive terms, I still get a 3 by 3 matrix. So, the second term I get is another 3 by 3 matrix, which I call B times the mid plane curvature K. Okay. And this is my force resultants. So, I can say that force resultants, which are nx, ny, nxy, are equal to A matrix, which is a 3 by 3 matrix, times mid plane strain, plus B matrix, which is a 3 by 3 matrix, times mid plane curvatures. This is one set of equations, and these equations connect force resultants to mid plane strains and mid plane curvatures. So, if for a composite laminate I know force resultants on the outside edges, if I know what is the value of force per unit length which is being applied, then I can calculate mid plane strain and mid plane curvatures using these relations. So, this is set 1. Similarly, so these are the relations for n's, right? These are the relations for n's. Similarly, let us see what we can do with the relations for m's. So, these are the relations for force resultants. So, now we do for moment resultants. So, how do they look like? We know that moment resultants mx, my, mxy are what? They are nothing but integral minus h by 2 to h by 2, and you integrate sigma x, sigma y, tau xy times z times dz, okay, times z times dz. Or in short, we can say that moment resultants are, this vector is equal to integral minus h by 2 to h by 2 of stress vector times z dz. Okay. So, this is just a short form, the second one, it just takes lesser space, that is all. but sigma, which is the stress vector, is what? It is q bar matrix for each layer. If I have to compute for at any layer, then what do I do? It is q times strain, and what is strain? It is mid plane strain plus z times curvature. Okay. So, I can say that m equals minus h by 2 to h by 2 q bar matrix times epsilon naught plus z times k naught, this entire thing multiplied by z dz. Okay. Now, using the same logic which we explained earlier, within a layer strains are constant, mid plane strains are constant and curvatures are constant, and also q bar is constant. So, I can integrate within a layer, but as I move from one layer to other layer, I have to add up because the function jumps, because q bar jumps from one layer to other. Okay. So, for a k layer laminate, this thing becomes summation of k is equal to 1 to n. Okay. And then if I am just doing my job for kth layer, then it will be q bar for the kth layer times epsilon naught plus z times. So, actually what I will do is I will move this z inside the bracket. Okay. So, then this becomes z times epsilon naught plus z square times the curvature vector, the entire thing we close the brackets times dz. Okay. So, this is my moment resultant, and this has to be integrated from h k minus 1 to h k. Okay. Now, within a layer when I integrate, then what happens to this z square? When I integrate, it becomes z cube by 3, and this z becomes z square by 2. Okay. So, what I end up getting is q bar. So, once I have integrated, I get q bar for the kth layer times, and when I apply limits on z square by 2, I get h k square minus h k minus 1 square by 2 times epsilon naught plus, if I integrate this, so I get h k cube by 3 minus h k cube by 3 k minus 1 times q bar matrix for kth layer times the mid plane curvature vector. Okay. And this is in a parenthesis. So, once again this is a 3 by 3 matrix, this is just a number. So, and this entire thing we have defined it as the B matrix earlier. This is the B matrix. Okay. So, this is nothing but B matrix. Similarly, if you sum up this thing, it gives you another matrix we will call a D matrix. Okay. So, I can say that the moment resultants mx, my, mxy are nothing but a 3 by 3 matrix times mid plane strains plus a 3 by 3 matrix called D times mid plane curvatures. So, we will write this more explicitly. So, this is Nx, Ny, Nxy, Mx, My, Mxy. So, if I have all the 6 relations, 3 force resultants and 3 moment resultants, then they are related to mid plane strains and mid plane strains, mid plane curvatures using these relations. And here this is a partitioned thing. So, in the first quadrant we have A matrix terms, okay. In the second we have in the third quadrant we again have B matrix, and in the fourth quadrant we have a D matrix. So, if you know the moments, force and moment resultants on the edge of a plate, then you can calculate all the mid plane strains and mid plane curvatures using the help of A, B and D matrix terms, and the definitions of A, B, D we have already described. Okay. We have already described using these relationships. So, what you have to do is you have to layer by layer compute these parameters and add them up for all the layers, and you will get individual A, B and D matrices. So, the A matrix is known as extensional stiffness matrix, and its terms are, you can say, GPa millimeters, because it's sigma x times, no, it's q times z, okay. The B matrix is called coupling stiffness matrix, and the D matrix is called bending stiffness matrix. It's called bending stiffness matrix. Okay. So, these are the definitions of A, B and D matrices. Tomorrow we will try to understand what is the importance of these matrices, and we will also maybe discuss a little bit some related things which help us standardize if we want to specify the lamination sequence of a composite. So, we will also talk about it. But that concludes our discussion for today, and we look forward to seeing you tomorrow. Thank you.